All right, good afternoon. Just continuing on with what we have with functions, and we left off last time with odd and even functions, and we have by definition, we have an odd function is a function whose relation where is going to be where opposite sign inputs will lead to opposite sign outputs, and thus we have the equation f of negative x is equal to the negative of f of x. Whereas in the case of an even function, we have f of negative x is equal to f of x. Now, for what we have on page 210, okay, we have starting out with number 34, and we have a function p of x, okay, set equal to the negative of the absolute value of x plus 12 times x to the 10 plus 5, and we're looking at determining whether that function is going to be one that is odd or even if either of these. Okay, so we have for p of x, okay, so we have p of x, again we have equal to the negative of the absolute value of x plus 12 times x to the 10th followed by the addition of 5. Okay, and we can just follow through on this one. Okay, so if I were to remove the absolute value notation, okay, now we have the absolute value of x. This would just go to x, and I'm still taking the opposite sign of this. Okay, so this would be the negative of x, and we have plus 12 times x to the 10th followed by the addition of 5. Now, in looking at the opposite sign input, okay, so I'm going from the input at x to negative x. So I have p of negative x, okay, and just in the case of the formula, okay, so we have the negative of the absolute value of x, we have the negative of the absolute value of minus x, and we have plus 12 times, okay, the 10th order of negative x, and we have followed by the addition of 5, okay, and again we have now absolute value of a positive is a positive, absolute value of a negative is still going to be a positive, so the absolute value of negative x is still x, and I'm still taking the opposite sign of this, so I have negative x. And for what we have for the 10th order of negative x, now a negative term to an even power will come out to a positive. So we have, so this will be x to the 10th and multiplied by 12. Okay, so we have plus 12 times x to the 10th. And we have followed by, okay, the addition of 5. Okay, and in terms of what is going on, okay, so now for the inputs, we got x and negative x. So you have opposite sign inputs. Now if you notice between the output terms, we got negative x, 12x to the 10th, and 5 for p of x, and for what we have regarding p of negative x, guess what? We also have negative x and 12x to the 10th, and also 5. And so it turns out that if we have opposite sign inputs for the function, that will lead to the exact same output. Nonetheless, this is going to signal that this function p of x is going to be one that is regarded as an even function. Okay, so this one, okay, so you have p of x here, okay, that is going to be an even function. And let me give you a bit of a visual on this one. And I'm going to take what I have in Desmos, and now we have for this one, okay, so I have, p of x functional notation for what we have in y. And again, that was, let's see, have the negative of the absolute value of x, and we have plus 12 times x to the 10th We have followed by the addition of 5. Okay, and if you notice with this graph, okay, now you're going to have symmetry with respect to the y-axis. Okay, so you have like on opposite sides of what we have of the y-axis. Okay, you have equidistant would be both halves. Equidistant from the y-axis, you have both halves, and you're going to have at the same level. Okay, because you have like maybe like negative and positive 0.587447, and we have at the other end we have again negative x or opposite sign x values, and we have the same y values. And for an even function, just to give you and show you how this might look, again for even functions, opposite sign inputs will have the same output. And if you notice, you have opposite sign inputs with negative and positive 1, and the outputs we have 16 and 16. Opposite sign inputs you have negative 2 and positive 2. And guess what? The outputs are the same. So if you have that kind of balance, like negative 3 and 3, still got the same outputs. Negative 4 and 4, still the same outputs. And so that is an indicator that we have, in this case, an even function. Now, for what we have for the next item, and this time we're going from p of x to k of x. And we have for k of x, that is set equal to 13x cubed plus 12x. And so we have here, so k of x, we have 13x cubed plus 12x. And again, we're going to look at the outputs on the basis of what we have with the inputs at x and negative x. So again, we have k of x is equal to 13x cubed plus 12x. And in the case of k of negative x, okay, so where we have x, we're going to replace with negative x. So you have 13 times the cube of negative x. We have plus 12 times negative x. And just, now, again, for the cube of negative x, okay, this will translate out to negative x cubed. And for what we have in the follow through, okay, so 13 times negative x cubed, this will be a minus 13x cubed. 12 times negative x, this will be a negative 12x. And I'll just duplicate what I have for k of x. Okay, so I have 13x cubed plus 12x. And just like what I had initiated for p of x that we have with k of x, I'm taking opposite sign inputs. And for the outputs, then we have positive 13, negative 13x cubed, and I have positive 12x and negative 12x. And guess what? So we have throughout, instead of being the same, we're going to have opposite sign outputs. So in this case, opposite sign inputs lead to opposite sign outputs. And so this means that for k of x, okay, this is going to be an odd function. So opposite sign inputs lead to unanimously terms in the output that will be of opposite sign. And just provide another bit of a visual. Okay, so for y is equal to 13x cubed plus 12x. Okay, now again, now the graph is going to have symmetry with respect to the origin. And just looking at some of the values here. Okay, so for opposite sign inputs, we have negative 1 and 1. And notice we have opposite sign outputs with negative and positive 25. And if I go with negative and positive 2, guess what? I have opposite sign outputs with negative and positive 128. And I can continue the trend, like negative and positive 3, as well as negative and positive 4, and I still get opposite sign outputs. Okay, so if you have opposite sign outputs for opposite sign inputs, that function is going to be odd. Okay. Now, for what we have in the case of 37, we now have a function in the form of n of x is equal to the square root of 16 minus, okay, the square of the binomial x minus 3. And for what we have in the setup, okay, so we have with n of x. Alright, so you have the square root of 16 minus the square of x minus 3. And I'll just go ahead and carry out the square of x minus 3. So I have 16 minus all of x squared minus 6x plus 9. And just spreading out and just displaying as the square root of individual terms in the mix that are unlike. Okay, so with the constants, we have 16 minus 9. So this will leave us with 7. And you have minus x squared. And we have minus 6x. So this will be a plus 6x. And you can rearrange the terms. But we'll just leave what we have for n of x as it is. So we had the square root of, in the mix, we have 7 minus x squared plus 6x. Now, if I take what I have for n of negative x, okay, so replacing x with negative x, okay, so we have 16 minus what's going to be the square of, not x minus 3, but negative x minus 3. And just step to the side here. Okay, so we have a negative x minus 3 squared. So you have negative x minus 3 times itself. And if I were to take the FOIL, okay, so you have negative x times negative x. Negative times the negative is a positive. And for the outside product, you have negative x times negative 3, so this will be a positive 3x. Negative 3 times negative x becomes another positive 3x. And negative 3 times itself is going to be a positive 9. So I'm going to have x squared plus 6x plus 9. And just referencing what we have in the radical. So I have 16 minus, and I have, again, same trinomial, x squared plus 6x plus 9 to deduct. And we have just combining the constants and distributing the subtraction. So again, we have 16 minus 9. So we have 7. And we have also minus x squared. And now the variable term of first order, okay, that's going to be a minus 6x. All right. And looking at how the expressions compare. Okay. So for x and negative x. Again, so these will be opposite sign. And if you notice, we have with the radicals now, these are positive square root terms. So those are the same. If you notice inside the radical now, we've got 7 and 7. Those are the same. We've got negative x squared and negative x squared. Those are the same. And upon first glance, it looks as if we're going to be on our way to having this to be an even function. So if opposite sign inputs lead to the same output, you're going to have an even function. But if you notice at the end, you got 6x and negative 6x. So those are no longer the same, so you have an opposite. So if you have the output to not be unanimously the same or to be additive inverses, you're going to have just an offset here. So if it's a blend of some terms being the same, some being the opposite, you're not going to have the function to be odd or even. But instead, this function is going to be neither. And just kind of taking what we have. See, we have with n of x or y, and we have c equal to the square root. Okay, and we have 16 minus the square of x minus 3. If you notice, we have a semicircle, but you don't have symmetry with respect to the origin, nor do you have symmetry with respect to the y-axis. And if I had the semicircle with, say, 3, 4 located instead of at 3, 4, if I had it at 0, 4, then you would have this to be an even function. But with what we have, you don't have either one, and just providing a bit of a glimpse. Okay. Again, if the function were even, you would have opposite sign inputs will lead to the same output. Or if I had an odd function, I would have opposite sign inputs lead to opposite sign outputs. And guess what? You don't have either trend occurring. Okay, so this particular function is one that is neither odd nor even. All right, and now for what we have in the case of 41. Okay, and we're looking at seeing whether this function is odd or even or neither. Okay, and this one we have with h of x is equal to 5x. Okay. So I have just a basic linear function. And just running through this very quickly. So you have h of x is equal to 5x. And for the input at negative x, so h of the input is equal to 5 times the input. So you have 5 times negative x, so this will go to negative 5x. And so with x and negative x, okay, so these would be opposite sign inputs. And for each of these functions, there's only one output, and we have when the input is at x, the output is at 5x, and then when the input is at negative x, the output is at negative 5x. Okay, and so if the opposite sign inputs lead to opposite sign outputs unanimously, okay, this means that our function is going to be one that is odd. Okay, so you have for y is equal to 5x. Okay, so you have a linear function that runs through the origin. So the graph will have symmetry with respect to the origin. And again, opposite sign inputs lead to opposite sign outputs. You have like for negative 1 and 1 for x, the respective outputs will have negative and positive 5. And say for negative 2 and 2, we have negative and positive 10. And again, still maintaining opposite sign inputs, you still get opposite sign outputs. So in this case, h of x equals 5x is still going to be, in this case, an odd function. All right, now in crossing over into the next realm, okay, and the other week we did look at samples, piecewise defined functions, and for what we have in the group for 47, okay, and we have a piecewise defined function. In this case, which we have given at f of x And this is made up into, this is partitioned out to 3 sections. So we have that y is equal to negative 3x plus 7 on the condition that x is less than negative 1. And we have in the next realm, the next tier, we have f of x is equal to x squared plus 3. And it's going to be for those values of x such that negative 1 is less than or equal to x, which in turn is less than 4. And then we have the f of x is equal to 5, and it'll be for those values of x that will be greater than or equal to 4. All right. And so we have with the determination of the various functions, for the inputs we have f of 3. Also we have f of negative 2. And then we have f of negative 1. Then we have f of 4. And we have followed by f of 5. And in terms of which of these 3 functional sections we're to be using, this is going to be contingent upon the inequality description. So for what we have in the case of f of 3, notice that 3 is between negative 1 and 4. All right, so negative 1 you have is less than or equal to 3, and that part is made true by the less than statement. And again, 3 in turn is less than 4, so I'm referencing the middle section. So in terms of what to do with 3, I'm going to take x squared plus 3, with 3 representing x. And 3 squared is 9, and 9 plus 3 is 12. Now for negative 2, now for the input at negative 2, now negative 2 is less than negative 1. That is a true statement. So applying on the condition that the input refers to the first inequality, we're going to use the first functional layout. So we have for negative 3 times x, this will be negative 3 times negative 2, followed by the addition of 7. Negative 3 times negative 2 is 6 plus 7, which is going to be 13. All right. And for negative 1 as the input, now negative 1 is not less than itself, but it is equal to itself. So negative 1 belongs in the second inequality description, just like 3 did earlier. And what makes this statement true, we have negative 1 not less than itself, but it is equal to itself. And negative 1 in turn is less than 4. And just like what I did with 3, I'm going to take negative 3. And in this particular case, all right, so we're going to have, like what I did with 3, I'm going to take negative 1 square out. And add 3. So we have negative 1 squared. So this would be 1 plus 3, which is equal to 4. And in the case of f of 4, and we're going to have the last inequality description to apply. And in this one, so we're going to have that 4, though it is not greater than itself, it is equal to itself. And in terms of applying the treatment for 4, well, we don't do anything with 4 because for anything that is 4 and greater, the output is equal to 5. Likewise, for the input value of 5, 5 is greater than 4. So we apply once again the last inequality. Again, we have the f of 5 is equal to 5. All right. Now, for what we have for the next piecewise defined function, and here we're going to have absolute value terminology that is in the mix. And we have for g of x. Okay, so for g of x, okay, we have for the, at the lower end, okay, we're going to have that y is equal to -2 times the absolute value of x, followed by the subtraction of 3. Okay, for those values of x, that will be less than or equal to -2. And then for what we have in the next layer, okay, we had that y is equal to f of x plus 6. Okay, for those values of x, that will belong to the compound inequality, where -2 is less than x, which in turn is less than 3. And we have for the remainder, okay, we will have that y is equal to g of x is equal to 4. For those values of x, that will be greater than or equal to 3. And we have for the various inputs, okay, so you have g of -3, we have g of 3, and we have g of -2, and we have followed by g of 0, and also followed by g of 4. Okay. And in terms of which of these three functional parts to work with, again, this will be contingent upon where the inputs will each belong. Okay, so for -3, -3 is already less than -2. So this will apply to the first inequality, and the function portion that corresponds, we have -2 times the absolute value, and this will be the absolute value of -3, followed by the subtraction of 3. Now the absolute value of -3 is going to be a positive 3. -2 times 3 is -6, and -6 minus 3 comes out to -9. Now for g of 3, okay, 3 not greater than itself, but it is equal to itself, and this last description is going to apply thanks to the equal section. And so for what we have in the case of g of 3, okay, so looking at what we have for the last, okay, so anything that is 3 or greater for the input, the output is going to remain fixed at the number 4. And for g of -2, now, okay, we have where -2 belongs, this will be with the first description, just like -3 earlier. And now -2 is not less than itself, but it is equal to itself. So we have -2 times the absolute value of -2, followed by the subtraction of 3. So you got -2. Now the absolute value of -2 is going to be a positive 2. And -2 times 2 is -4. And with the subtraction of 3 to follow, okay, we have -4 and -3, so we have the output to end up at -7. And for what we have for g of 0, now 0 is situated between -2 and 3. And so corresponding to this compound inequality, I have 5x plus 6 with x at 0. And 5 times 0 is 0 plus 6. So we'll have that g of 0 is equal to 6. Okay. And for g of 4, okay, the input we have at 4. And 4 is greater than 3. And so for all the values of x, okay, from and including 3 and going on up, okay, again, the y value or the g of x value is going to remain fixed at 4, and that will be the last output requested in number 48. Now, for what we have in the case of number 50. Okay, this time we have another application of the functional notation where we have y is set to t of x. And for what we have among the categories, okay, so you have with t of x. Okay, first of all, I have t of x is equal to x, and it'll be for those values of x such that 0 is less than x is less than or equal to 1. And then we have, for the next portion, we have that t of x is equal to 2 times x if we have that 1 is less than x is less than or equal to 2. And we have t of x is equal to 3x. And so for those values of x such that 2 is less than x is less than or equal to 3. And finally we have t of x is equal to 4x. For those values of x such that 3 is less than x is less than or equal to 4. Okay, and so we have with the various input values. Here we have t of 1.99. Okay, and for 1.99, that's going to fall between 1 and 2. Okay, so 1 is less than 1.99, and in turn we have 1.99 is less than 2. So we're going to apply the 2x portion, and with x at 1.99, we have for 2 times 1.99, okay, we have that the output is equal to 3.98. Okay, now sort of shifting gears. Okay, now we're going from 1.99 for the input to 0.4. And 0.4, this will belong to the first compound inequality. So 0 is less than 0.4, that is true. And 0.4 is less than or equal to 1, that is also true, thanks to the less than portion. And in this case, t of x is equal to x. Well, guess what? With x at 0.4, t of 0.4 is equal to 0.4. Okay. And we have for t of 3, okay, and where 3 belongs, you're going to be hunting down the equal sign referencing 3, and this will be with the third compound inequality. And so for what we will have here, okay, so we have that 2 is less than 3. That is true. Less than or equal to 3. And that compound inequality is true thanks to the equal. And so we're going to take what we have for 3 times x. Okay, so we have, so for t of 3, that is equal to 3 times 3. And that is equal to 9. Okay, and we have for t of 1, okay, so for x equal to 1, okay, we have referencing 1, okay, and that which will include 1 will be that statement that has the equal to sign along 1. Okay, so you have less than or equal to 1, and this will be what we have in the case of the first compound inequality. So we have 0 is less than 1, that is true, and while 1 cannot be less than itself, it can be equal. So again, so we have for t of 1, okay, that is in reference to t of x is equal to x. So with x at 1, we have that t of 1 is equal to 1. And then we have for the last of these inputs, we have 3.001. And for 3.001, okay, that is going to be greater than 3. So we'll be referencing the last of the compound inequalities. Okay, so we'll be looking at the utilization of 4 times the input. And so in this case, your t of x with x at 3.001 is going to be equal to 4 times 3.001, and this will come out to 12.004, and that will be the outcome for this remaining piecewise defined function. All right, and now there are some graphing features we do have regarding functions. Okay, and now sections 160 to 180 in ALEKS, okay, those are going to be sort of graphing intensive, but for the second test, and I'll give an announcement regarding that. It's not going to involve graphing, at least nowhere as much. And for what we have in the concepts, okay, now we're going to have what we refer to as minimum and maximum values. And for this portion, okay, we'll have what we regard as relative minimum and maximum for increasing and decreasing functions. Yeah, it's a little bit of a long title, but there are lots of things going on simultaneously. Okay, so have relative minimum and maximum for increasing and decreasing functions. And we have, let's give you an instance. Okay, and just kind of applying a graph here. Now I'll just assign some order pairs here. Okay. Okay. And we'll say we have something like -1, -5. And we'll say we have -3, -2. And see we have -4, -4. And we'll see we have -5 and -1.5. And see we have out to the right. Okay, we'll say that we have, see we have 4, 2. And 5, 0. Okay, first of all, let's say on the side of what we regarded as relative minimum. Okay, and let's say that I know there's some ALEKS items, and some of the terminology can get a little bit confusing. Like, you know it conceptually, but in terms like what it's asking for, like the verbal part of it can get a bit confusing. Okay, and now let's say first of all, okay, if I'm looking at determining, the relative minimum of f of x. Okay, and what this means by relative minimum, think of like minimum. Okay, you have like a bottommost point, and for the points of interest. Okay, so for what we're going to have here, okay, for the relative minimum, you're looking at the y values of those particular points. So you can just kind of call those the minimum. It's kind of like conceptually as the dips. Okay, so you have like so you have here the function going up, then it's going down. So you got a y value over here, and then we have they have rise again. Then you have to bottom out again, and then you have rising up. Then you have bottoming out. You have going up once again. So minimum is where you're going to have a decrease followed by an increase, and that point in between the decrease and increase, that is going to be a minimum. Okay, and so for your y values, you have -4, -5, and also we have at 0. And we have for the second question, okay, it says determine the values where the relative minima will occur. Okay, and I know I meaning to answer like the y coordinates, which I guess in a sense technically it is correct, but for what Alex would be asking for, like the values where the relative minimum will occur, it's actually asking for the x values. So for what we have in the case of the x values where the minima occur, now again the minima we have at -4, -5, and 0, and for the x coordinates we have -4, -1, and also 5. And it doesn't have to be like it can be not necessarily in that order. You could also have them occurring in increasing order, kind of like samples of ordered pairs. We just kind of like, you can have like the domain in jumbled order or ascending or descending order. Same thing for the range. Now, and let's say that for this same function f of x, I'm just going to reapply this, okay, and just sort of look on the side of what we have in reference to the peak points, that is the maxima. So you have for this third part, okay, so you have okay, so if we're looking at determining the relative maxima of f of x, again, so for the relative maxima, okay, those are going to be your y values. Okay, and so we have for the relative maxima, okay, now we have for your maxima, okay, those are essentially going to be the peaks, the relative peaks. Okay, we have an increase immediately followed by a decrease. Okay, so for your y values, you have a peak point here, another peak point, and another relative maximum over here. And so for the values of y that correspond, okay, so reading in order from left to right, we have negative 1.5. And also we have at negative 2. And also we have at y is equal to 2. And if I were to determine the values, where the relative maxima will occur, okay, and so we have, again, referencing the x values. Okay, so again, we have our peak points. Again, the maximum values had at negative 1.5, negative 2, and 2. And for the corresponding x values, okay, we have at negative 5. And also we have at negative 3. And also at positive 4. So again, where they occurred, this will be the corresponding x values. Okay. Now, again, just for the introductory part, okay, we have relative minima and maxima for increasing and decreasing functions. Okay, now on the side of what we have concerning activity, that is motion. Let's see. There we go. Okay, so we have regarding motion. Okay, so if I were to determine the intervals, the interval or intervals where the graph of f of x is strictly increasing, okay, and you're looking throughout the real number system, and you're focused upon the x value, so just from end to end. So you have starting out from, looks like x approaching from negative infinity, and then we have expanding on out to x approaching positive infinity. And where we have increases, that is if you read from left to right, so we have upward motion, you have an increase, then you have downward motion, then we have another increase, followed by a decrease, and then we have for the next round, you have an increase. And the next phase, okay, we have another increase. And the intervals where f of x is strictly increasing. Okay, so we're looking at going from negative infinity, approaching negative 5. And where we have increases and decreases, you're maintaining the use of parentheses. So between negative infinity and negative 5. And then we have going past negative 4, approaching negative 3. And then for what we have with the remaining increases. So we have between these 2 points. So we have between -1 and 4. We have also in terms of increase, we have going past 5 and approaching infinity. All right, so we have increase here, here. Okay, and also between -1 and 4, and also for values of x that will be greater than 5. Okay, and also in the determination of intervals. Whereupon f of x is going to be strictly decreasing. Again, for increase, decrease, okay, you're not going to have any brackets in the interval notation. Okay, so where we have decreases, okay, so going from end to end, so you have a decrease, another decrease, kind of like a sawtooth pattern. Increase, decrease, increase, decrease. Okay, so for the x values I'm concerned, so you have between -5 and -4, also between -3 and -1, and also we have between 4 and 5. So for these intervals, strictly decreasing, again we have between -5 and -4. You have also between -3 and -1. And finally, for the last layer, okay, whereupon we have the function f of x to be strictly decreasing, we have between 4 and 5. And again, we have parentheses throughout. Right. And now, and let's say that if we have for a given function, okay, and we'll say that for what we have in this graph. Okay, let's say that So we have determining the following. It's kind of a repeating pattern. Say we're looking for the relative minimum. Where the relative minima occur. Also we have the relative maxima. Also where the relative maxima occur. Also, we only got, okay, the intervals. Of strictly increasing. And also the intervals of strictly decreasing. Okay, so for this function, f of x, okay, again, let's see what we get for the relative minima and maxima, and also where both types of entities occur. And also, let's see what we get for the intervals of where f of x is strictly increasing and also where it is strictly decreasing. Okay, for this particular graph, okay, for f of x, okay, if we go ahead and identify the relative minimum, okay, so you're going to have, again, we have the relative dips, so to speak, the dipping points. And so those will be the y values that correspond. Okay, so we have, so for the relative minimum, okay, so you have y equal to, so again, we have 0.5, -2, 0.5, and if you got any repeating y values, you just had to put down only once. Okay, so we have, in this case, we have y at 0.5 and -2. Okay, so those would be your relative minima values, 0.5 and -2. And where the relative maximum will occur. Okay, so we're going to have, in this case, right, so those would be your x values that correspond. Okay, so we have, so you got 4. So again, for your lower points, okay, so you have 4, -4, 0, and 3. Okay, so you have 3 distinct x values, whereas in the case of the minima and y, there are only 2 distinct values since 1/2 repeated. Okay, now for what we have in the case of the relative maximum, okay, same graph, okay, and different items we're looking for. Okay, so you have your relative peak points, and there are going to be only 2 of these. Okay, and so we have for the relative maximum, you're looking for the y values and where the relative maxima will occur. Again, we're looking for the x values. So for the y values, you have 2.5 and 2, or 2 and 2.5. Order does not matter. In the case of what we have for x, okay, we have negative and positive 2. And that's where the relative maximum will occur. All right. Now, in the case of what we have for the spread from end to end, okay, where we have the intervals strictly increasing, okay, for the given function. All right, so you have for the increases throughout, okay, so you have reading in order from left to right, so you have an increase, then you have a decrease followed by the next increase, and for the rest of the activity you have another increase. And for the items of concern, so the first increase you have between -4 and -2. Next increase I have between 0 and 2. And then we have for the remaining increase. Okay, so we're starting at this from this point. Okay, and we have going past 3 and proceeding out in the direction of infinity. Okay, so you have again from -4 approaching -2. And then we have between 0 and 2. And then with this last layer, we have going out past 3 and proceeding out to infinity. And for what we have in the case of strictly decreasing, okay, so you have for downward motion, you have decrease, you have an increase, and then you have another decrease, you have another final decrease. And for what we have here, so you have going from negative infinity approaching -4. You have next, you have going past -2 approaching 0. And finally we have going past 2 approaching 3. Okay. And so for the interval notation, you're referencing just the x values involved, not the ordered pairs in x and y. So these would be what we have for the intervals of strict increase and decrease. Now, just one other key feature we have regarding f of x, and this will be what we have concerning the category of turning points. And for a polynomial function, okay, and say we have for a polynomial function, now we have for f of x. Now the notation will appear to be theoretical, but it's going to serve a purpose regarding the number of turning points. Okay, so you have polynomial function, you have f of x is equal to a of n times x to the n plus a of n minus 1 times x to the n minus 1. Okay, say for a polynomial function, okay, and the terms will be in descending degree order. Okay, so the degree of the function is going to be n. The number of turning points will be at most n minus 1. And another way of phrasing this is that the degree of f of x will be greater than the number of turning points. By at least 1. Okay, and just to kind of cue you in terms of the number of turning points. Okay, see we have for the number of turning points. Okay, so we have like, so this will be your combined relative minima and maxima. Okay, so you got one minimum, second, okay, we have a maximum, third, we have a minimum, fourth, we have a maximum, and fifth, we have relative minimum. So counting up your total minima and maximum, okay, we have 5 turning points. And with 5 turning points, now this is going to signal that in terms of what the degree of f of x could be, okay, so number of turning points will be at most 1 less than the degree of the function. And if we got 5 turning points, then that means that the minimum degree of the function will be 6. But it could also be 8. It might be 10 or some other higher even number if it's not 6, 8, or 10. And where turning points will kind of correspond to the degree of the function, I'll just kind of throw in some other cases, and I'll just do kind of a quick sketch among these. Okay, and say if we have okay, so just counting up all the relative minimum and maximum. Okay, so in this case, there are going to be 7 turning points. And from this, now for the degree of the function, okay, and the degree of the function is always more than the number of turning points. So it could be 8, 10, or some higher valued even number. It could be 12 or 14. And let's say we have something like so you have a graph, okay, and we have for the number of turning points, again, combining the total number of minimum and maximum. Okay, so here, we're now going to have 4 turning points. And for the degree of f of x in correspondence, Okay, so the minimum degree of f of x, okay, it's going to be one more than the number of turning points, so it could be 5, and if it's not 5, it's going to be a higher valued odd number. It could be 5, could be 7, could be 9, but some odd power that is greater than or equal to 5. Odd higher value or higher odd value. Okay, so again, the number of turning points is always going to be less than the degree of the polynomial function itself.